Let me welcome all of you. It's a really pleasure to welcome you here within the frame of the DEXA conference. And we arranged an interactive discussion forum with this smart title, Big Minds Sharing Their Vision on the Future of AI. Okay, and for this we invited key researchers with a special background, but from different angles. Okay, and I want to welcome here. Yeah, you see the names of the slide. It's Battista, Biggio from University of Cagliari in Italy, Sardinia, with security adversarial machine learning. Then Claudia Diaz from Belgium, from the Catholieke Universiteit Leuven, also with security, but some different aspects. Then there is Olga Saukh, a young researcher from Technical University of Graz and the Complexity Science Hub in Austria with more environmental aspects. And last but not least, okay, Heiko Paulheim from the University of Mannheim, who is a specialist in knowledge graphs, graphs embeddings. Okay, and I want to start. My person, maybe some words. I'm Bernhard Moser, so here from Austria. I am with the Software Competence Center Hagenberg. This is a research and technology organization here in Linz, also close to Linz in Hagenberg. I'm research director there, and I'm also with the Austrian Society for Artificial Intelligence, ASI, okay, and currently I'm the president there, which is a academic platform for research in the field of AI in Austria. Okay, so let's start with, let's say, so I'm giving the word to the guests, okay, and yeah, so that they introduce themselves, and let's start with Heiko.
Okay.
Please.
I think you have to unshare the screen so that I can show some slides, if that's possible.
Can you?
I think you can just start the screen sharing, your co-host, okay. So it should work.
Okay. I see.
Otherwise, let me know.
Oh yeah, okay, fine. All right, so yeah, thanks for the invitation. My name is Heiko Paulheim. This is the University of Mannheim you see here. Unfortunately, we are not in this fancy castle, so computer science is in an ugly 70s building, but we still use that as a boilerplate slide just to make people jealous how nice Mannheim is, which it unarguably is. Okay, so when I was asked to like share my vision on AI, I thought some years back when I was attending an AI lecture at university as a master's student, and we used this book by Russell and Norvig, Artificial Intelligence, A Modern Approach, which I think many of you are familiar with. And yeah, in the very beginning of this book, the authors say, well, what are the ingredients for AI? So to pass a Turing test or to provide general AI or something like that. And they say, well, there is actually 4 things you need. You will need natural language processing so that the machine can interact with you in the way that humans interact. You will need some knowledge representation so that the machine can share, access some knowledge. You will need automated reasoning so that the machine can do something with the knowledge that it stores. And you will need machine learning so that the machine can adapt to new situations and the like. So these were the 4 components. And yeah, then I was curious to see where are we in terms of that. And I was looking at a Google Trends evaluation. So I used these keywords, natural language processing, knowledge representation and reasoning. That was one topic in the Google Trends, and machine learning, which is also a topic in the Google Trends. And so here you see the graphed search results on these topics over the last 15, 16, 17 years. And it seems like it's a massively unequal world we're facing here. So machine learning is skyrocketing, especially with the new hype on deep learning in the past decade. Whereas natural language processing and especially knowledge representation and reasoning, they are much, much lower. So it looks like if we need these 4 components in to build an AI, one could say, well, in terms of machine learning, we're pretty safe, but what about these other fields? So why do people give them comparably little consideration? And then in the course of another work, I stumbled upon this paper at which was shown at AAAI 21 by Booch and others, who used this famous book by David Kahneman, Think and Fast and Slow. And they said, well, actually, this can be transferred to AI as well. And in AI, you also have these 2 systems. So what Kahneman does in his book, he says the human mind has 2 basic subsystems, which he calls system 1 and system 2. System 1 is the one which is predominant in terms of it's intuitive. It's what you do all the time. So where you need no cognitive efforts to use it. So for example, when you see a person, you know it's a person without any active thinking about that. Whereas when you need to think, well, where do I know that person from? You will need some activity, some explicit thinking, and that's system 2. So and Booch et al. Said, well, actually, you see these 2 systems also at work when you look at AI systems. So system 1 is this thing which uses statistics and heuristics and also machine learning models, which are based on statistics and heuristics. So this is pretty much what system 1 does in the human brain, whereas system 2 would be more the stuff with knowledge representation, where you have some explicit knowledge representation, where you do some explicit reasoning, which you can also understand how you got there, which provides you with an explanation. So when you run a reasoner and say, I want an answer to that question, you always get like a proof tree, for example. So this is system 2. This is very explicit. And well, in the recent days, you see a lot of works in the direction of combining these components, like machine learning, heuristics, statistics on the one hand side, explicit knowledge representation and reasoning on the other hand side. You see those under the monikers of neurosymbolic or hybrid AI in these days. And what you may also recognize when you read Kahneman's book is that he said, well, system 1 is the one which we use most of the time because it's effortless, but it also has a lot of dangers. It leads us to all sorts of biases. And then you think back and will say biases in AI. Well, this is also a topic these days, right? So people say, well, AI might be biased. And this is especially, in my opinion, due to that overly focus on system 1 like AI. And you saw that in the previous slide, there's huge bulge of interest in machine learning as compared to comparatively little interest in these system 2 like AI components. Nevertheless, people look into these system 2-ish AI ingredients, as I'd like to call them. So in the 80s, there was this project called Saukh at Saukh, which was like the first attempt to distill a certain amount of the world's knowledge into a knowledge base where you could also do some reasoning. The inventor that day, Douglas Leonard, he also invented its own language, like the Saukh language, which allowed you to formulate rules and do all sorts of explicit reasoning on these facts. With the advent of linked open data, people put all sorts of massive knowledge collections out, like DBpedia and Yago, which are automatically created knowledge bases, like Wikidata, which partly uses crowdsourcing, partly links to other data, and also this massive linked open data cloud. So you have a huge collection of knowledge from all sorts of domains, all sorts of areas of interest, ranging from bibliographic data to general knowledge to biological knowledge and so on and so forth. So a lot of that data is actually out there, and you can use it to fuel AI systems and give them more of a system 2 flavor, if you like. So these very recently, they've been becoming more famous under the name of knowledge graphs. So knowledge graphs are graph-shaped representation of knowledge. So when you have an AI, like the one which runs on your smartphone, and you sit at home during lockdown this summer and say, hey, Google, when is the final season of Money Heist going to be on Netflix? And there's lots of things that go on under the hood, and some of those things, apart from like trying to understand this question and synthesizing a spoken answer, a part of that is actually needing access to knowledge, like Money Heist being a series which has some parts, and these parts have release dates and so on, and then mapping the parts of the question to those information in the graph and giving you an answer to your question. So actually these things are in use in modern AI systems. So there is a big chance here, because if we use these knowledge graphs in AI systems, we don't need to start them from scratch. We don't need to put like this pure machine learning based systems where you put like a blank page AI out in the world and let it learn about the world. You can actually start on a much higher level with a lot of knowledge of the world that people have collected over the years. So when you look at these knowledge graphs that I just mentioned, DBpedia and the like, you have open data. You can use them. You can just put them into your AI to make it start from a higher level, so to say. They know like billions of facts that the AI has immediate access to. So what the AI then has, it has a lot of factual knowledge that it can use to provide answers, also to provide explanations. This is one huge area of research these days, how we can make the AI explain itself, how it got to a conclusion. And at least for like post hoc explanations, these knowledge graphs can be of great value. One of the challenges is that people have been dealing with in the recent years when trying to build such hybrid AI systems is that these knowledge graphs, I mean, they are graphs. They are called knowledge graphs since they are graphs. And when you want to build something which has a learning component and some knowledge component, you need to build a bridge between those worlds. And most of the learning tools that people have these days are expecting something like tabular data. So they want each entity to be like a vector in an n-dimensional space, so to say, whereas these graphs, they are not like that. So what people do to that is they try to learn some vector-like representations from these graphs. And there is all sorts of approaches around there. So people have done adaptations of language modeling techniques like RDF to VEC, for example. This is an adaptation of word to VEC for knowledge graphs. They use tensor factorization. There is all these words on link prediction in geometric spaces. There is more recently also graph neural networks. And what all of them do is they take these graphs and turn them into vectors so that they can be fed into a learning system. So you would think, well, this gives me one of these AI systems at the end of the day, which has both of these system 1, system 2 components. It can learn because it has all these nice vector representations, which can also be learned in themselves. And at the same time, it also has access to this explicit knowledge representation. But when we step back a bit, it seems like we're again missing something here, because these knowledge graphs, they are so popular because they can be consumed by humans and machines alike. They build a bridge between the two. So when I see a knowledge graph, and you saw this example with Money Heist, I as a human being can understand what's in there. So if the AI provides me explanations based on that knowledge graph, it can explain itself to me, and we can also build an AI which I can like interact with on a level where I also understand what it does. When I have just a vector, I cannot do that. A vector is just a point in a 100-dimensional space. So I say, well, if that is the explanation, it doesn't give me a lot. So what we actually do with these embeddings, to put it a bit more provocatively, we actually take a system 2 in Kahneman's terms and forge it into a system 1. So we throw away all the explicit reasoning and we just make it a point somewhere in a space which has no meaning anymore, which can be very conveniently processed by these system 1-like systems, which do all the statistics and the like, but which misses all the explanation and all the interpretation and all the semantics that we put into the knowledge, into the AI in the first place. So one of the holy grails, in my opinion, in that area is to create embeddings or representation learning systems which still retain this idea of being interpretable, so that we can communicate with the AI, and then by that have an AI which has both these system 1, system 2 like components, but at the same time is also interpretable for us and understandable for us. So this is like my take on possible future directions on AI. I'm looking very much forward to the other introductions and the discussion.
Okay, it's one view into future. So let's move to our next guest, Claudia, please. You are muted. Claudia, you're...
Hello?
Yeah, no.
Oh, okay. I'm sorry. Okay. So everything is visible and you hear me. Okay, good. Yeah, I was saying that I am not an AI person. I am actually working on privacy, but we also use AI as part of our methodologies and tool sets. So that's the perspective that I'm going to give. I'm going to talk a little bit about metadata, traffic analysis, and where AI comes into the picture in this application. So first of all, what is communications metadata? So it's everything about data that you're communicating that is not the content. So for example, who's sending the data, who's receiving the data, at what time is it sent, how long it is, and if you have repeated communication patterns, that also can be part of the metadata that, for example, I send you a message every day at 10 p.m. This data is actually exposed by default by internet protocols. So TCP/IP exposes the source on the origin and the time and the length. Well, the time is implicit in that is when it's being sent. HTTP, UDP, DNS, all of these protocols, even though many of them make an effort to protect the payload with encryption, they do not protect the metadata. So that means that this metadata is available to a number of intermediaries. This includes some big players such as internet service providers, internet exchanges, autonomous systems, internet backbone. So these are kind of all the big players in the internet, but also smaller players that might control a little piece of the infrastructure you're connecting to. Like, for example, the person controlling the Wi-Fi router or the local area network or any eavesdroppers at any point in the communication between you and your destination, which can be at the other side of the world. And we saw, like a few years ago, with the revelations of Snowden, that actually a lot of the NSA programs were focused on the collection and analysis of metadata, not least because metadata is very easy to read by machines. It is lower volume than the content. So for example, if I'm downloading a video that is multiple gigabytes, the metadata would just be, the time when I'm downloading it and the name of the file, some identifier of the file, how long it is and so on, and that's it, which is much less than the actual data. And it's also because it's not natural language, which we already heard that we are not so advanced in having machines understand human language. Metadata is actually machine language because it's, it's all of these very specific fields. So it's actually very easy to interpret and analyze automatically. And on top of that, it has lower legal protection than data content. There are laws that protect legally data content. You cannot just look into the communications of other people, but metadata is not quite as protected. Okay, so what do we do with this? In research in the last 3 decades or so, we have had a number of proposals for protecting this metadata from eavesdroppers. The goal of these systems is typically concealing who communicates with whom and obscuring communication patterns so that it's not possible to infer private information from analyzing these communications metadata. The architectures, these are typically networks, and the architectures of these systems for private communication are typically overlaid networks with multi-hop routing. So that means that your communications are sent via a number of intermediary proxies that transform this communication with some cryptographic operation, which provides this per hop bitwise unlinkability. And then they relay the communication to the next intermediary, which might be the final destination or another intermediary until it gets to the final destination. So you're not talking directly to your final destination anymore, which makes it more difficult for an eavesdropper who sees you talking to see who you're talking at the end of the day, because they might see only that you're talking to some intermediary. For example, if you're using Tor, you'll be talking to your entry guard in Tor. There are 2 main types of solutions. There's onion routing solutions. I'm sure many of you are familiar with Tor. These are circuit-based solutions, meaning that you use public key cryptography to establish a circuit through these intermediaries. And then this is a bidirectional channel through which you can send and receive information back and forth that is encrypted with symmetric keys that are established when you're building the circuit. And Tor and other onion routing solutions typically do not add latency. So as soon as they receive a packet, as soon as possible, they forward it. And this is why they are specifically targeting applications with low latency, such as web browsing. A different type of solutions is mixed nets. Mixed nets are packet-based. That means that they treat every packet individually. So every packet has to have the addressing of where it has to be sent eventually. So all the headers information has to be, you don't just establish a circuit and then send data through the pipe. Every packet is its own self-contained. This means every packet is unlinkable from each other. It's more difficult to perform traffic analysis. On top of that, mixed nets add latency. Every node adds latency to the packets it routes. So that means that it becomes even more difficult to track inputs to outputs. So these are the main two types of solutions that we have. On top of that, you can add dummy traffic to further obfuscate communication patterns. Okay. So where does ML come into the picture? So when I think of ML and anonymous communications, I mean, of course, there is a lot of work. I mean, a lot can be done with vanilla communications. If you don't have any protections, I'm sure you can get a lot of intelligence by just, applying machine learning to patterns and stuff. But once we have systems that are kind of security systems that try to make this difficult, then we enter into an interesting arms race between methods for protection and machine learning trying to still defeat those methods of protection to still infer useful information for the adversary. So the two main attacks, and these have been studied quite deeply for Tor. The two main attacks are, the first one is what is called end-to-end correlation. So basically here, what it means is that if I am able to see the beginning of the circuit from the user to the first entry node, I'm also able to see the end of the circuit from the exit node to the final destination, even if I am not able to see what is going on inside the Tor network. I might not see these connections between the onions. I am able, with machine learning, some people have proposed solutions that do this, with machine learning, that they're able to correlate the input to the output. So basically, even though Tor is kind of routing things through these intermediaries and the timings get a little bit disrupted, this disruption is not enough to make it difficult to correlate the traffic when it comes in and when it comes out. So Tor does not try to defeat against this adversary. It's built for a weaker adversary, but yeah, mixed networks are actually built to defeat this adversary, and it's an open question whether this kind of attack would be effective in a mixed net or not. And we're actually now doing work on that. So we'll have an answer. We don't know yet. We'll have an answer in a few months, hopefully, whether machine learning is powerful enough to extract information, the little information that is leaked from these communication patterns, or whether the system is strong enough in obfuscation that the information that is leaked is not enough to make these correlations. The second attack is more interesting because this is a weaker threat model that even Tor should be protecting against, so is aiming to protect against. And this is what is called website fingerprinting. In this variation, the adversary does not have access to the exit of the network, only to the entry of the network. And basically what it does is that it has a set of target web pages that it wants to identify. So first the adversary builds like a database of fingerprints by using the system to download these pages, makes a database of fingerprints by extracting features from these pages. And then when the target user is using Tor, you can analyze the traffic and see whether the traffic pattern in the user to Tor connection matches any of your fingerprints. And if it does, there is a very high likelihood that the user is downloading the web page that you think he's downloading, that is matching the fingerprint. So this actually defeats kind of the main purpose of Tor. Therefore, it's an important attack, and there is a whole body of work looking into countermeasures. How can we protect against this, and how can we make better attacks? So just to conclude, some of the challenges when we look at the metadata and ML. Basically, the things that make it very difficult to protect against ML-based analysis is that when we have very diverse type traffic patterns, they become distinguishable. The features are different from one user to the other, and then it becomes difficult to have users be confused with each other, which is what we want to have communication privacy. Furthermore, if users have persistent communication patterns, this is hard to conceal over the long term, because even if you're having protection that there is kind of noise, the signal to noise ratio kind of goes down as you repeat the action over and over again. So this is very challenging, how we can protect persistent patterns from this kind of ML techniques. Defeating these techniques would require tolerating more latency, which is terrible for usability and can completely kill some of the applications, because people are not willing to wait for many applications that should be interactive. Or you can spend more resources with covered traffic. And the question on how we can build cheap and usable and efficient communication networks that are robust towards these ML adversaries while still being suitable for general usage is pretty much an open question. That's all I have.
Okay, great. And next, Claudia. Very, very interesting. So that's a risk we have to face. And now let's go on with Battista and then Olga, please.
Okay. So good afternoon, everybody, and thanks, Bernhard, for the invitation to the panel. So I'm Battista. I'm from the University of Cagliari. I'm assistant professor there, and I also work. I'm a co-founder of a spin-off company of the university, which is called Pluribus One, where we develop solutions for cybersecurity tasks based on machine learning. So this basically reflects what I've done in the last 10, 15 years. So working, in between machine learning and computer security. That's why you have this machine learning for security and machine learning security in the title. So where the for is optional. The thing is that this has been somewhat discussed before also by Heiko, that we have now let's say very powerful AI systems, which are essentially based on deep learning, on this kind of system one, where they emulate the sensor level. But these are also very accurate, and let's say with respect to what has been done, in the symbolic literature many years ago, things have really started to work nowadays when we were able to collect large amount of labeled data and with enough computational power to train these systems. Conversely to what we thought, emulating the human reasoning, because that's a much harder task than it was one. So now we have something that works at an acceptable level, and this is embedded in many tools that we use nowadays. You can even talk with your mobile phone, and this is quite accurate in general. But I'm here today, and I think I've been working a lot of time on this just to show that many of these algorithms may have failure cases which are difficult to envision. So AI or deep learning seems to be smart, but it's not something that we can trust in all situations, at least. Now, I'm sure you've heard about adversarial examples because they are a very popular area of research. I'm just giving here some prominent examples that were, let's say, showcased in the field. And here, some authors have shown that you can actually fool a face recognition system by just wearing some fancy glass frames, where the noise that you see on the frame is actually crafted in a way to fool the learning algorithm. And in this case, Leo Bauer, which is one of the researchers that authored this study, was trying to impersonate Mila Jovovich. And so this is just to give you an idea of the kinds of error that we may achieve with this algorithm, so that you may enforce with that. Here you have another example where traffic sign recognition can be fooled. So for instance, here researchers from UC Berkeley have shown that you can actually paste some stickers on the stop sign to have it misclassified as something different, like a speed limit. Here in the video, you have an example. On the left, there is this modified stop sign, which is consistently misclassified as a speed limit, whereas on the right, it is classified correctly. Again, here, the stickers are not put there at random. There is a specific optimization that you have to do to design that. There are examples outside of the image domain. So also for a system that aim to transcribe speech to text, you can fool them. So for example, here I'm playing a small audio. And you will see the transcription by Mozilla Deep Speech on the right.
Without the data set, the article is useless.
And then this is what it is transcribed by the algorithm. You should have learned it, I hope, listening. And now I'm gonna play a slightly modified audio where we as humans will perceive essentially the same sentence, but you'll see that the algorithm will transcribe something very different.
Without the data set, the article is useless.
So in this case, this background noise, again, which is optimized against the algorithm, let the Mozilla Deep Speech understand something completely different, which is like, okay, Google, browse to some malicious website. And the sentence which is transcribed is essentially in the hands of the attacker. So you may craft hidden commands to your Alexa or whatever in order to do something weird or malicious. So those are just examples of just to showcase the problems. But it's not the only threat that you can target against AI. So I've been talking against attacks that can be crafted against a deployed system. So you already built your machine learning model, you deployed it in practice, and then the attacker can manipulate data in a way to fool it somehow. But there are many other kinds of attacks that you can have. The attacker may also tamper with the training data used to learn your system by implanting backdoors or creating problems to legitimate users when they will try to use the system during operation. Or there are attacks that can be staged also against deployed services, but to fool, to get confidential information out of that. For instance, you can query services which are provided online, possibly to steal the model which is used by the company, and maybe offer a competing service at a lower price because you steal all the intellectual property in this case, if you steal the model. Or you can also infer confidential information about the training set and the training data which was used to build the system, which may again unveil some confidential properties of the users of the system. So this is just to give you a panorama of the problems that may be out there. And the general issue is that AI is vulnerable because some of the underlying assumptions that we have for this system is essentially violated in these settings. And this is really well described in a few words that were spoken by Bernhard, where he acknowledges that the fact that these systems work well when the data that you collected to build the model, like your training set, is representative enough of the data that you will encounter during operation. This is also called the IID assumption or the stationarity assumption behind machine learning. So for tasks where we have been able to collect enough data, like image classification or speech recognition, basically we have covered a lot of cases, and then the system works pretty well in many different conditions, even if not in all cases, of course. But still, we are not yet at the point in which you can deploy an agent, throw it in the outside world, and say, okay, now this is going to work in all cases. So, like a self-driving car may have, encountered scenarios that are never envisioned before, so that are not properly represented in the training set, and this may create problems, and you may have unreliable decisions in this case. Adversarial attacks, are just the extreme example of this condition, where you try to use machine learning out of distribution, in a sense. And so I think this is the challenge for the future, because in practice, this implies that the performance of these systems will decay over time. For example, this is an instance of Android malware detection, where you see that something which is deployed at month 1 works very well, but then decays very quickly over time. And the only strategy that we have nowadays is to retrain the system periodically. But we could do much better, especially if we leverage what the engineering community is doing to automate the deployment of machine learning. So if you think to software engineering, which is much more mature than machine learning as a field, there you have tools for writing code, checking if vulnerabilities are present, automatically deploying updates. You have repositories that keep track of the backup versions. We have a lot of tools that help us speeding up the process. And this is a trend which is also now being followed in the machine learning area. So there is the analog of DevOps for software in machine learning. It's called ML operations. We are trying to automate the creation of models collection of data, training, packaging, validating, and deploying. And this poses many industrial and research challenges as well. For example, how do you manage like continuous data ingestion and labeling? Think to a cybersecurity problem, like you have to create an anti-malware solution. There are new viruses coming up every day, and then you need to collect the labels and update your data systematically. And there is no clear approach on how you deal with noisy labels or potential delayed information, all these kind of things. There is the challenge on how to update the model. For example, to avoid regression problems. That means if I have a model now, which is correctly classifying some examples, I don't want that the updated model makes mistakes that were not made before. So we should have also this regression testing in place, as we have for software engineering, and there are many other issues that come out of this problem, including the lack of debugging tools and systematic security testing to understand if attacks are possible and how. By debugging tools, you can also think to explainability of the models, as Heiko was saying. This is something we can use to debug if there are biases, for instance, in your training set. So you can use some explainability form to this end. So my vision for the future is that we should try to bridge this development cycle by adding it with some security properties, working on data and model preparation to ensure that the model is protected against some of the threats that you can envision, at least during design. You should have testing mechanisms in place to check if your model is vulnerable to adversarial examples or other attacks in your specific application. And again, here, there is a huge area of research because AI is an enabling technology. So you should have a model which depends on the application. How you perturb data depends on the application. And then we should also take care of monitoring how the model is operating. For instance, if there is an attacker which is repeatedly querying the model to get information out of it, like trying to exploit the service in different ways. And this is all lacking nowadays. But I think it's a good opportunity for joining a research which is in between industrial and more fundamental issues. And that's all from my side.
Thank you. That is highly relevant. Okay, then we move to Olga. Okay, and after this, we will have an open discussion. Please.
Hello, everyone. Hello, Bernhard. Thank you for the invitation. Can you see my slides?
Yes.
Okay, great. So I'm Olga from Computer Engineering Institute at TU Graz and the Complexity Science Hub Vienna. I'm the fourth one to present, and I'm really very happy that I can actually show you yet another perspective on the topic, which is really great. So I work on problems spanning computer engineering, Internet of Things, technology on the one hand, and how this technology can address pressing problems of our society and environment on the other. So let me start this presentation by acknowledging actually the progress machine learning made over the last decade. In this plot, this is a very famous plot, you can see the progress on image classification task. So you can see on the x-axis a year of the ImageNet competition and the best classification accuracy achieved in that year. And as you can see in the beginning, basically people thought it's a very difficult problem to solve. You can see as well 1,000 classes, a very large data set, and early methods didn't really do well. So they achieved around over 25% error. Then in 2012, actually the AlexNet, the breakthrough happened, and convolutional networks showed that they can make a lot of progress on the problem. And as you can see, so in the following years, convolutional methods were improved, and the networks got bigger, and also more computational power was involved. And according to some measure, well, taken with a grain of salt, of course, we now have a superhuman performance in ImageNet. You can see human error is about 6%. Many companies joined in, the winner from 2014 came from Google, from 2015 from Microsoft. There was also a huge money investment, partly due to this progress on the ImageNet. Progress on machine learning was also boosted by the following trends, nicely summarized by Jeff Dean, the head of Google AI, in his talk. So the results get better with more data, bigger models, and more computational power. And let's have a closer look into these three ingredients of success. So more data means better or good benchmarks, and this is very helpful to make progress on the methods. However, ImageNet is a toy example, and most interesting data sets actually can't be gathered faster and can get outdated. If you think of environmental data sets where some dynamic changes of the environment is present. So no matter how fast you sample, you can't get any measurements from the future, right? It's also very difficult to understand in these large data sets, what are the biases that are present in this data. Now, what about bigger models? On the bright side, the progress that we made in terms of network architectures is indeed real, as the literature shows. For example, one recent example is a successful transformer model. Yes, a lot of progress is achieved by increasingly large and computationally intense deep neural network, deep learning methods. An even sharper trend can be actually observed in the natural language processing community. You can see this in the table, the fresh statistics over the past 2 years, where the dataset size increased factor 50. And the number of model parameters, well, 4 orders of magnitude. And I mean, over 2 years, and 2021 is not yet coming to the end, right? So this trend is both environmentally unfriendly and, of course, expensive. And finally, regarding compute power, so we have entered a new age characterized by the slowdown of Moore's law and end of Dennard scaling. And given the rise of big data applications, it brings serious challenges that computer scientists and computer architects should face or must face. So further improvement to transistor density and power becomes more difficult, and also financial cost of computation and energy should not be underestimated. Interestingly, or better to say ironically, deep learning was inspired by the human brain, which is remarkably energy efficient. I would also like to touch upon the aspects of AI that go beyond environmental footprint, were also mentioned actually in the previous talk, such as dependability, explainability, safety, robustness, adaptation, and fairness. So impressive progress on machine learning help us makes us hope that we can now use machine learning in high-stake domains, basically safety critical applications such as in transportation. We are talking about self-driving cars, robotics, industrial robots, or healthcare applications. And if we go beyond these simple applications and more towards this high-stake domain, then then we actually need to make sure the technology that we build is reliable and can be trusted, and it is a responsible technology. So a few facets of my future vision. So I think that it's important that we make a conscious effort to look into research directions that do not depend on larger and larger model and that are more computationally or environmentally friendly and inclusive. For example, sparse models. If you think of it, the world we live in is not dense, it's actually sparse. Also, the connections in our brain are sparse and not dense. We also leverage locality at all levels. However, sparse models as we build today they actually, first of all, generate overhead because of the sparsity as a structure. They also amplify biases and increase model vulnerability to adversarial attacks. Appear difficult to train and adapt. I also think it's important to invest in good, accurately annotated data sets. Robustness to small, natural occurring distribution shifts is a performance dimension that is not covered in current benchmarks. That's why the existence of all these adversarial attacks and so on. We also should gain a deeper understanding in the input changes a model should be robust too. So in summary, I think we need accurate and capable data-driven systems that have minimal negative impact on the environment. So AI has been widely recognized as a key technology to solve pressing problems of today, such as climate change, environmental sustainability, global public health, infrastructure, and resource management. And in my final slide, I would like actually to compare AI technologies that we use to optimize and manage the problems at global scale to the ways our brain, sensory inputs, and actually the pain mechanism manage well-being of our bodies. So if something goes wrong, we feel pain and we react immediately. So we can view pain as a crucial survival mechanism, or we can view data and machine learning models as an extension of our sensory capabilities beyond our bodies to help us make smart decisions. So towards this end, my vision is that we can, that we succeed to interpret these weak and noisy signals coming from the environment correctly and in time for a sustainable future. Thank you. That's all.
So thank you very much. So, and in the end, it's up to all of you, yeah, to bring questions. Of course, there are so many topics and deep topics which is not possible, yeah, to discuss them in depth, all of them, yeah, in half an hour or so. But please let us start. Okay.
Bernhard, may I start the discussion?
Please, yeah.
Okay. So I'm Mohit, working for SCCH in the direction of privacy preserving machine learning and trustworthy AI. So just to start the discussion, may I ask Olga about trustworthy AI? You know that you mentioned about EU guidelines regarding ethical AI. Now, these 5 principles of ethical AI, they have been adopted for trustworthy AI. But these principles have inherent contradictions in themselves. For example, the one principle asks you to preserve the privacy of the data, make the model beneficiary to whole humankind. So privacy and sharing of the model, copyrights, then the explainability versus accuracy. And so there are inherent contradictions. So in your opinion, what would be the way forward to have trustworthy AI-based systems? I mean, as an machine learning developer or as an AI engineer.
Mm-hmm.
Thank you. This is a very good question, and I don't see this actually as a contradiction in terms of it can be avoided. They're broadly formulated, and there are more than 5, I believe.
Yes, 5.
Yeah, they're broadly formulated, and I believe the way forward is actually to bridge the gap, because right now the way we test systems before we do something about them is actually, it's very limited, right? It's either you test on your, maybe on your data or on your very artificial setup, basically, or even virtual setup, and then you deploy. but somehow there is a disconnect, right? Because we don't have an understanding what happens out there. Take self-driving cars, right? They are tested extensively in the field, many kilometers, to basically update the model. But this is a specific field. We don't do this testing for other AI systems actually out there. And self-driving cars are not yet there, right, out there. So I believe the way forward is actually to bridge this disconnect between how we test the system in our artificial environments that we have actually at our disposal for testing, and the real world. I also mentioned that so in the data that we use to train model, there may be biases. We don't understand actually what the trained model should be robust to, right? And gaining this understanding, it's also aligned with this bridging the world between how we test the systems and the real world.
Yeah, thanks. Just a last comment. For example, a automatic CV screening system, for example, is rejecting automatically the CVs of women. So it's a bias. There is a bias in the model, but this bias the model has learned from data itself.
Absolutely, you know? Yes.
So that's what
there
the
are no
machine learning is
surprises
supposed to do. I mean, now what could be done against that?
Okay. Who wants to comment on this?
Yes, I think you have to mean biases at large, like that your training data can also be biased.
Yes.
Because of course, if you have all examples of CVs of women who are rejected, then you have a bias in your data as well. So it's not only a problem of the model; it's a problem of the design phase at large.
And Battista, you talked about this data poisoning attack on the machine learning pipeline, and can you suggest something against that? I mean, if someone is poisoning data, is differential privacy is a solution to that?
So in general, I would say no, because differential privacy is to enable a different mechanism. But there are defenses against poisoning attacks in general. Depending on the kind of attack and the kind of application, they are more or less effective. Yeah, so you could do something. The only thing is that there is an inherent trade-off on how quickly the algorithm can adapt to learn new data. With respect to how it reacts to poisoning. So there's this trade-off which has to be taken into account. But if you don't need to frequently retrain your system on fresh data, then probably you could do something.
Okay.
May I react to the CV parsing question as well?
Yeah.
So back in the 1970s, 80s, machine learning was mostly stuff like decision trees or rule-based systems, right? And when you have a decision tree and you have a branch which says if the candidate is female, reject, everybody would just scream and say, well, no, we can't use the system. Nowadays, we have deep neural nets and nobody knows what they are doing. So you don't know whether this candidate has been rejected due to her gender or due to some other properties which might be legit reasons to reject that candidate. So this is why I think this is why also these neurosymbolic AIs come up so much these days, because as soon as you have some symbolic component which can tell you why the AI system does what it does, then then you can sort of mitigate as well. Of course, there is all sorts of challenges from how to build these systems on. Maybe if you incentivize the training of the AIs in a very, very bad way, you might even have an AI which deliberately provides you with wrong explanations. But I don't want to be all too negative about that. So I'm pretty sure that this worst case Skynet scenario doesn't need to become reality, and you can really at least mitigate that problem to a certain extent using that neurosymbolic integration. You can probably not fully circumvent it with it, but you can at least make it a bit less severe.
Okay, so Battista, you listed some assumptions, mentioned by Bernhard, IID assumptions and so on, And on the other hand, with linked data, okay, it's going beyond these assumptions. Maybe this is really an argument. But what's on the other way around, okay, so we're also by neurosymbolic hybrid systems, we're getting even more powerful AI. And so what does this mean for Claudia's problem?
So is the question for me?
Okay. For you, Battista, I think Claudia, because there's this problem with metadata, okay, and with ML, we can, so to say, make some attacks,
I think that, so this is one thing that is something that we are investigating as well. So there are ways that you can use to bridge, let's say, the power that you have for learning from data with, the domain knowledge that we have on the other hand. And the problem is how to combine these things. So if you can, for example, bring some constraints from domain experts and make them, enforce them in the learning process from data, because some things, I mean, the algorithm will learn everything that is there in data, but things that may happen that and are not contained in your data set, they cannot be learned. So you have to try to enforce this external knowledge into the process. I think it's very promising. There are ways that you can do to, for instance, take logical formulas, convert them into loss functions, and build your models. Now, in security, the challenge is whether you have this knowledge a priori and whether you can enforce it in the model. But typically, I'm very skeptical when I see deep learning in cybersecurity tasks, because that's absolutely vulnerable. But so typically you see the systems that are mostly used are, again, the classical end feature extraction step, and then some simple learning algorithms, which you can understand what's happening.
I want to respond to that. So, yes, so the one of the interesting things about I don't think it came across because I didn't make it explicit, but one of the interesting things about the example I showed of website fingerprinting and end-to-end correlation is that in this case, the classifier is the adversary. Okay, so we are inverting the roles. We're inverting the roles. It's not that the classifier is the system and the adversary is trying to create an adversarial example to fool the system or to make the classification fail. We're actually reversing the roles, with the adversary being the classifier, and then the defense system has to fool the classifier, right?
No, it's as I understood it, it was an offensive ML case.
Yeah. So in that sense, but I am not sure there are so many examples where the designer's task is to make the classifier fail. I'm sure there are other examples in other applications, but I think this is quite neat in that it kind of presents a scenario where the tables are a bit turned, and you're trying to make a system that you cannot learn from it because the adversary is the one learning.
Just out of curiosity, are there works where you have AIs on both sides? So an AI attacker and an AI defender playing against each other?
Not in this context, but we might get there. I mean, in other contexts, my understanding is that yes, this adversarial, networks, whatever. Not in traffic analysis, in the sense that traffic analysis is a complicated one because you're depending on these end users and what they want to do, right? Like you cannot even count on them being online, and then you can generate dummy traffic at will. So there's like all of these constraints coming from these players. Like how would it work, right? Like if I am not even online, how is my phone now going to generate some traffic pattern or things like that? So yeah, there are many real world constraints that make the problem very complicated.
Actually, there are three issues. The one is the security of AI or machine learning model. The other is AI or machine learning model for the security. And the third is how could we use AI for the security in general? So that's more relevant issue. Can someone tell us something about that? How in the future AI could be used for security or for trust, for building the trustworthy system? I mean,
general.
It's not about the security of AI system, but the other way around. How to use AI for security.
I
But
mean, I think this has been done
already
in the
there.
past, right? Like anomaly detection. It's all about that, right? Like you use AI to detect patterns that are suspicious.
Yeah.
So
there are many companies that do these things.
Yeah, vulnerability detections also.
Okay. So I think security was one thing, is of course a crucial topic. The other one is Olga mentioned in her presentation. It's about what can AI contribute to pressing problems of our humanity, environmental problems. And there you mentioned, okay, that we need sparse models. Okay, so I think this is also a link to Heiko, to your approaches on lightweight knowledge graphs. Maybe you can shed some light on this. What is the future of AI? Is it getting bigger and bigger and bigger, or do we manage to get some sparse and some lightweight models? Also to get a green AI.
It's at least the easiest thing you do. So if you want to take the easy way, you just do more of the same, which just means you just add another layer to the model, right? Usually it's like in mathematics, that the small and elegant proofs, they are the ones that take the most thought. But I think there is still room for that. So if you think of these big neural nets, and on the other hand side, you may have some big knowledge graph which is there, which is actually also accessible and explicit, then you can maybe outsource some of that. So that's some part that the AI doesn't actually need to learn because it's already there. So the neural net then can focus on the parts which are not already explicitly given. And in that sense, I think, this can also lead to smaller neural net models or statistical models, system one models, whatever you like to call them. So if you manage to find a way to tell the neural net, well, this is the part you don't actually have to learn, you can just focus on these and those aspects, then I think there is a big chance in also getting like more sustainable models. Because on the other hand side, then this explicit model, of course, this can be shared across tasks, across different models, and all these specific neural nets, they just need to focus on their own specific tasks.
I very much agree with that. I also think that so on the one hand, this is what you mentioned, and it's about the sparsity, but it's about inference, but it's also about updating the model, because right now we train end to end, right? And sparsity would mean updating locally, and this is something that is completely non-existent. At least we don't know how to do this.
Federated learning, right?
But you update the whole model, actually, right?
Goes in that direction.
I mean, local updates, so update only part of the model, and the rest is still somehow valid. And, this way of
Okay, Makbul, you have a question?
Hello.
Hi.
Can you hear me?
Yes.
Yes. So my name is Makbul Khan. I'm working also in SCCH and assistant professor at Austria, Pakistan, Fakhashule. So my question is about the AI system future jobs, about the normal people like undergraduate level and someone like for data science, we have the data scientist job like junior data scientist, similarly for software engineering. So what my question is for all the panels, that about AI future market job for, I'm not talking about researcher or PhDs, but for the low level, for the university level, how you can see that?
So you mean whether AI will replace jobs in the AI industry itself?
No, I mean like AI, if we study someone at undergraduate level, like BS in AI, and because he is not like a researcher to do some, but if he want like a software engineering, if he has BS in software engineering, the major, and like in BS data science, they have the data scientist, because AI system are developed in high-tech companies, but for the normal market, if it's not in the high-tech zone, is there some possibility like in SMEs for small and medium-sized enterprises, there are jobs about the artificial intelligence, especially the AI system engineering?
I could imagine it's going to be like with SAP. So there's just a small number of people who develop SAP, but there's a huge number of people who like customize SAP for end users, right? For small companies who want to use SAP to, I don't know, do invoicing or HR administration or whatever. I could see the same thing happening for AI, that you have some major vendors of AI solutions, but you cannot just take this AI solution, put it in a company and let it work. But you need some customizing, I don't know, like domain specific adaptation and the like. And I could see that sort of job being done by these, how you call them, like bachelors in AI.
Okay, means like some customizable system, if they have, then they can do it like for the SMEs to be customized that system.
Yeah, because there is like no off-the-shelf AI that you can, I have a problem, I buy an AI, I put it on the problem and the problem is solved. So it's not, that's not how it's going to be.
Pluribus is such an example. Yeah, it's an SME. And I think in future, okay, like GDPR, yeah, there will be an AI regulation. And yes. I think many companies will need some consultancy, some support, setting up the systems, testing, and also what Battista mentioned with this pipeline of ML DevOps. Yeah. Okay, this needs a lot of engineering. And
yeah, even if you think, I mean, when you have to collect data from different databases or sources, there is a lot of work that you have to do to prepare the data to be, fed to the AI.
Okay.
So, thank you.
Thank you, Makbul, and also all of you. It's only 1 hour, so but I think to have such a panel and with different. Let's say views. It's I think, to my opinion, it's a good format. Instead of just single presentations, I would like to continue, but I think it's now at the end of our hour. So I would like to continue this maybe in some other frame. So I really want to thank you, and maybe you contact us by email, and put questions, or let's keep in touch.
Thank you very much for the invitation.
Yeah.
Thank you.
Thank you.
Thank you.
Thank you. Bye bye.
Bye bye.